In this video, I'll show you how to build a self-contained portable solar-powered inverter. I'll be upgrading an existing system, but you can build this rig from scratch by just ignoring the part where I removed the old inverter. I use my rig for remote video shoots, and it powers my video camera, a teleprompter, and a reference monitor. I'm Ken Walker, and on behalf of Omega Sanctuary, if you'd like more off-grid tutorials and articles, please subscribe to our channel, like our Facebook page, and visit our off-grid website at omegasanctuary.life. Alright, so the main housing uses a weatherproof tool chest. The solar panels have already been installed on top. We'll be using a number of new components, including meters and gauges, and I'm using a 1500 watt pure sine wave inverter. If you're going to be powering sensitive electronics, you want to make sure that you use a pure sine wave inverter, otherwise you could damage your devices. I already mentioned we're upgrading this rig. Currently it has a 400 watt inverter and no monitoring capabilities, so we can't look at the battery level or charging efficiency of the solar panel. All the existing components are going to stay except for that actual inverter. Alright, so the first thing we're going to do here is I've left all of these cables long because I knew at some point I was going to be upgrading this. So we're going to disconnect everything. Number one, that makes it a lot safer to work on. But number two, we're going to be moving things around and rearranging. So let's get the inverter out. And this is just a standard cheapy kind of inverter, you know, something that you might find at a truck stop or Walmart. It's just 400 watts. It's a modified sine wave, so it's not good for sensitive electronics. The next thing I'm going to do here is use some 1-inch aluminum bars as mounts for the new inverters. And I drill holes in the bars to bolt the bars to the chest, and then I drill holes in the bars to mount the inverter to. Now I'm just taking my Dremel tool and cleaning up the burrs from those holes. All right, now here the inverter has been mounted to the aluminum rails to the back of the chest. I've already marked the spot for my first panel meter. I'm gonna cut that out with a Dremel tool and then clean it up with a utility knife. Basically, I want to verify that the fit is going to be good. The tool chest material itself is kind of thick, so I want to make sure that the panel meter is going to fit in there snugly. Now I'm cutting a hole for the inverter's remote power switch, and what that's going to do is allow me to turn the inverter off and on without opening the chest. All right, now I've got the inverter connected to the battery so that I'm going to be able to test the remote switch, make sure it turns the unit on. So I connect one end of the included cable into the switch. Then the other end I connect to the inverter. And then I go ahead and confirm that when I operate the switch, the remote switch, it does in fact turn the inverter on and off. Now that I've got the remote switch installed, I go back, mark all of the spots for the other panel monitors, and we're going to be monitoring the efficiency of the solar panel. We're going to monitor the load that's on the inverter, so we'll know exactly how much energy we're consuming as we use the unit. And we're going to monitor the charging and discharging, so we'll know if the solar panel is producing more power than what we're using, as well as how quickly we are discharging that battery or using up the stored power. And here we've got all 4 panel meters installed. Next up, I've moved the solar controller to the other end, so now I want to go ahead and cut the solar panel feed lines to length so I don't have a bunch of extra cable. I will mention I installed the controller upside down because I want to have easy access to the connections and I want to be able to feed the lines in from the top. After the solar panel connections are made, I move on to the positive terminal on the battery. Let me point out, I'm working indoors. Okay, so the solar panel itself isn't going to produce much power at all, but I'm basically positioning all of the components and then cutting wires to length. If you're working on a live battery, remember, be very careful with your tools and the cables inside of there. You don't want to create a short by connecting a positive and negative terminal together. Next, I move on to the negative battery terminal on the controller. One end of that wire goes to the controller, the other end goes to a shunt. And I apologize that the shunt is out of view here, but as you'll see shortly, I'm going to be mounting that to the inside of the chest. Now, I've connected the factory end of my cable to the negative side of the battery. This cable also goes to a shunt, and I added a terminal connector to the end of it. So I'm going to crimp it now, but I will later go back and solder that connection. Crimped connections are great, but the way I see it, if it's a permanent installation, might as well go ahead and solder it. So shunts are used because they allow us to take voltage and current readings across the known resistance of the shunt. Okay, and you'll see how that comes into play here shortly. But I've got a shunt going from the negative side of the inverter as well. And once complete, those two shunts are connected in series, essentially end to end. And make sure you go ahead and check the wiring diagram if any of that is confusing. Now, here's a better angle for installing the shunt from the negative side of the inverter, and I'll point out these shunts are for DC systems, okay? Typically, they're installed on the negative side of the power circuit. All of the shunts in this rig are connected to the negative side of the circuit, and they're connected in series. So you are essentially connecting the negative side of the battery terminal through 3 different shunts to the negative side of the inverter. Let's take a little sidestep here for just a minute, and I'm going to show you some basic soldering procedures. For making the connection from shunt to shunt, I want to use an exact fit cable, and if you do a little bit of shopping, you'll see that it's really hard to find this type of cable in a specific size already. So I'm going to go ahead and fabricate those myself. Now, we're dealing with a 12-volt system that's really capable of handling hundreds of amps. So the cabling for this part needs to be pretty heavy. It needs to be just like the other cables that you're using to make your main connections from the battery to the controller and from the battery to the inverter. So it needs to be automotive cabling. For an inverter over 500 watts, really, I would recommend using 4-gauge wire anyways. So that means that the connectors that you use, they have to fit a 4-gauge wire, okay? So keep that in mind. So slide on your heat shrink first, okay? Because the other end of this cable already has a factory end on it. So I'm just kind of, I cut it and I'm gonna reuse it and make my own cable here. You wanna make sure that you're using rosin core solder. That's for electronics. That means that rosin is already inside the solder. But I am gonna go ahead and add some here just to help the solder spread a little more quickly. I couldn't find my project arms, so that normally holds all this stuff in place for me. So I had to improvise with the clamp and the bolt there. Now what you want to do is put your heat source on one side of the connection that you're soldering, and then apply the solder from the opposite side. And what that does is it forces the solder, as soon as it melts, it starts to wick towards the heat source, and that means that it has to move through all of those metals. It has to permeate those gaps, and that's going to give you a much stronger, more solder filled connection. So once the solder has cooled slightly, then go ahead and slide the heat shrink tubing up, and then just apply heat and shrink it to fit. Do it just enough basically so that the tubing stops shrinking. And when you're all done, you get what's comparable to a factory-made cable. Next up, we're ready to go ahead and wire up the panel meters. And as you can see here, I've numbered each one through 4, and that corresponds to the wiring diagram that I have for you guys as well. So make sure when you wire these that you're working on the right panel meter, okay? Number 1 is gonna measure the performance of the solar panel. Number 2 is gonna measure the charging performance. And number 3 is gonna measure the discharge performance. And then number 4 is gonna measure the load that's being drawn from all the devices that we're powering. All right, up next, we're gonna get started with number 1. That's mostly gonna be going to this shunt right here, okay? We are also gonna run a wire to the positive terminal side of the battery as well. But what that means is that all 4 wires from the meter will be in this general area. So I've cut all of my wires to length, and I do want to let you know, make sure you use color-coded wiring with this, okay? Otherwise it's going to be very difficult to sort this all out. But the process is simple. One end of each wire will go to the terminals on the panel meter right here, okay? And the other end gets a connector. So we just strip the end from the wire around 3/16 of an inch or so. And let me mention also, these wires don't carry a lot of current, okay? So they don't need to be heavy. These can be just regular solid strand 24 gauge wire. Okay, now on the other end, we're gonna solder those connectors. And the process for that is the same as what I showed you earlier with the heavy gauge wires. So strip the wire, slide on heat shrink tubing, crimp the connector, solder the connector, then pull the heat shrink tubing up and apply heat. So now we need to go ahead and connect the green wire from panel meter 1 to the shunt connector that's directly connected to the charge controller's negative battery terminal. But we need to be on the opposite side. So go from the controller to the shunt, and then connect the green wire to the opposite end of the shunt. Next, we're going to connect the yellow and blue wires from panel meter 1 to the side of the shunt opposite to the green wire, okay? Just like in this diagram. Once that's done, you can go ahead and temporarily connect the red wire from panel meter 1 to the positive side of the battery, but this is a temporary connection, okay? Because we're gonna be joining all of the red wires later on to a single connector, so it'll look a lot neater. So connecting it now is just to verify that the panel meter is working, and to be honest, I haven't used these meters before, so I wasn't sure on the orientation, so I wanted to go ahead and activate one of the meters so that I could see if it is in fact oriented correctly. And once that is active, we can go ahead and check it. And in fact, it is upside down. So I'm gonna have to rotate all of these meters 180 degrees. For the next phase, I'm running all of the wires from each of the other panel meters, but to keep things nice and neat, I'm combining some of the wires. So for example, if you look at the wiring diagram, you'll see that the green wire from meter 2 can be connected to the yellow and blue wires from meter 3. They're all going to the same terminals, so combining the wires with one single connector makes for a much cleaner installation and uses less hardware. And since I've got all of the panels installed now and I've got all the wiring cut to length, I'm combining the red leads from the panels to a single connector that goes to the positive side battery terminal. Next up is hooking up the number 4 panel meter. For this one, the green wire goes to the same side of the shunt as the negative side of the inverter. Always double check the wiring diagram, okay? Because it doesn't necessarily reflect the exact physical layout of these components. The yellow and blue wires are connected to the opposite side of that same shunt, okay? And then the red wire for number 4 is already connected, and we can see that the panel is now active, okay? And that red wire is connected to the positive side of the battery with all the other red wires. Once that's done, we're gonna tidy things up a bit and install some cable organizers. So start at the longest reach of the wire, snug things up a little bit. We want to allow for some flexibility, but we don't want anything to be taut. Then drill a hole, stick the bolt through, slip the wires into the clip, and tighten the nut. Okay, now that we know exactly where the battery is going to be placed, I'm going to go ahead and drill some holes for the battery mount. Can't quite reach in between here, so I'm going to just mark it, slide the battery over a little bit, and then drill my holes. Then I go ahead and drill some holes in the lid, and I'm doing this so that I can just use some cable ties and strap those solar panel wires down nice and keep them out of the way when opening and closing the lid. Okay, so at this point everything is connected. You can see that I'm at 12.5 volts here. No energy usage really to speak of, okay? But that's because this is just the unit. If I turn the inverter on, you can see right away we've got power consumption. The top right hand meter here is actually the load meter. I'm going to be labeling them here in just a minute, but with the inverter turned on, that meter registers a 1.57 amp load consuming 19.5 watts. And again, that's the inverter itself simply powered on, nothing connected to it, not running any accessories or other devices. And that's why you want to have that remote switch so that you can turn the inverter on and off and save your battery draw. Now I've got the rig outside. The panel is facing the sun, and I can use these brackets to match the angle of the sun. The top left meter shows us how the panel is performing. So let's go ahead and check the system now with a load. So now I got a fan running here at full speed. I've gone ahead and labeled the panel meters as well. So with that fan going, the load on the system is 58 watts, just under 5 amps. So I'm going to go ahead and turn the fan off and watch the load drop. The power drops down to 16.789 watts. The current drops down to 1.35 amps. And this load again is just the inverter itself. So let's turn the fan back on. And now I'm hitting at a little over 5 amps. I think it's going to drop back down. And power consumption around 57, 58 watts. So if I'm running with a 1500 watt inverter, I got quite a bit of headroom for some other devices, right? Let's take a look at charging though. So with the fan on, no charging is happening, right? The panel's not able to produce enough power. But even if I turn that fan off, still no charging, okay? So again, that's because the inverter itself is still consuming too much power. So to get an accurate reading on the charging, we need to turn the inverter off as well, because again, it consumes more power than the panel is producing right now. So with the inverter off, we're charging at 1.3 amps and 16 watts. All right, now you may have noticed that to test a load on this system, I plugged a fan directly into the inverter, okay? And that's fine for a test, but for normal usage, obviously we need to have receptacles on the outside of the unit. Now, most inverters in this class are gonna have receptacles. I'd prefer terminal posts so that, you know, I could directly hardwire my own receptacles. But since I've already got a receptacle on the inverter, I'm gonna go ahead and use that. So I'll be using a plug and some 14-2 wire. Now I've also got an outdoor cover for my receptacle. And this receptacle includes USB connectors, so I'll be able to charge my phone and, you know, some of the other devices that use USB charging. One cool thing about the rig at this point is that it's actually active, okay? It's working. So I'm gonna be using the solar power that has been stored in this battery to operate my tools and complete the installation. With the opening cut out now, I'm gonna just mark and drill some holes at the top and bottom. The receptacle itself already has bolts in place for that, so I just use those to make a mark, then drill the holes, and then the receptacle mounts flush. All right, so now that the receptacle itself fits, I'm just gonna give it a little more strength and stability by drilling through and putting a couple of extra bolts and securing those with nuts on the other side. Now with the receptacle installed, the next step is to make that connection to the inverter. So I want to go from the inverter, run the wire down and around, and then back up to the receptacle. You're going to cut the wire to a rough length. Leave enough extra, okay, in case something comes up, and we'll just trim that off later. To install the plug, strip a couple of inches of insulation from the end. Remove the end of the plug. Loosen the clamp. Stick the wire up through the clamp. Don't clamp it down yet though. Strip off about 1/4 inch to 3/8 from the black and white wires. I like to put a slight hook at the end just to give it a little more grab. Go ahead and slip that in, hook it, and tighten it down. Do the same for the ground wire. Hook it, tighten it down. Then repeat for the black wire. Slide the plug cover up. There's usually some type of key or a shape arrangement that lets you know that it is in the right position, okay? So don't force it. Push that connector back in, tighten it down, and then you can go ahead and tighten the clamp side. I want to stress something here. Do not plug this in. Okay, don't connect this to the inverter, because if you do, this end becomes hot. That means you could get electrocuted. So if you want to get an exact fit here, what I recommend is that you disconnect the inverter. I'm going to go ahead and just shut the inverter off, and then we'll fit that wire. But again, just for safety's sake, even though I know that the inverter is turned off, I'm gonna unplug this to work on the other end and trim it up and get it ready. So we strip the ends and go ahead and slip them into the terminals and tighten them down. All right, so just a couple of things I want to mention. One is that a ground wire is actually redundant in typical house wiring circuits. Its original design was as a backup in case the neutral wire shorted and failed. So that way there wouldn't be a direct connection from a hot wire through your body, for example, to the ground. So, but if you go look at the breaker panel in your house, you'll find that the neutral wires and the ground wires all terminate on the same block, so they are connected, okay? So in a system like this, where we aren't actually connecting to a ground because it's portable, it just rolls around, the only thing that could be done, and you don't have to do this, okay? But if you wanted to, you could locate a grounding terminal on the inverter and you could connect that to a jack on the outside of the rig. And then you would need a grounding rod that you could plug into that jack and then drive that grounding rod into the ground several feet. I'm not gonna fool with it, but I just want to let you know it is possible. Now, since I don't want a box inside, a receptacle box taking up a bunch of space, because I've planned for growth and I want to be able to add additional batteries inside. But I also don't want people getting, accidentally bumping a receptacle and getting shocked. So I'm putting a couple of wraps of electrical tape around the outlet again, just to cover the terminals. Not trying to make this waterproof, just want to keep people from bumping those wires. Our next upgrade is going to be an exhaust fan. This is going to be thermostatically controlled so that if our battery gets too hot, the exhaust fan is going to kick on and cool things down. So what I did here is I position the fan and just drill one hole, and I'll just mention, make sure that you check inside the box to make sure there's no wires or anything else in the way before you do that drilling, okay? But I put that one hole there, and then I slip a bolt in the hole, and that helps me keep it in position so that I can drill the next hole. And then I'll put a bolt in that second hole, and that's going to help keep the fan from rotating or sliding around. This is simply because I don't have a paper template to use or anything. But now I can drill the other two holes, and now I can also trace the inside of the fan, which is where I'll be cutting with my rotary Dremel tool. All right, so once that is all cleaned out, you need to check your fan. Okay, the fan is going to have an airflow indicator that lets you know which direction air is going to go with the fan in operation. So I've got a hole on the other side of the chest right behind the inverter. So when the thermostat turns this fan on, cooler air is going to be drawn in through that hole. It's going to go over and around the inverter, and that hotter air is going to be blown out through this exhaust fan. So now the thermostat is going to get installed inside the box as well. The red and black wires on the thermostat go directly to the corresponding battery terminals, but the yellow and black wires on the thermostat are going to connect to your fan. You're going to have to cut the wires from the fan, and you're going to probably notice that the fan wires are red and black as well, so don't get things confused here, okay? The red on the fan goes to the yellow on the thermostat, and the black on the fan goes to the black on the thermostat. And then again, the red and black on the thermostat itself go directly to the battery, okay? And I'm just soldering these connections. We're not doing any crimping or anything like that. I'm just soldering these and then applying heat shrink tubing. And guys, make sure that you check out the wiring diagram if you have any confusion at all about how these connections are made. Now we're going to go ahead and make the terminal connections from the thermostat to the battery. Same process as you've seen before. Slide on your heat shrink, put the connector, crimp it, solder it, and then apply heat to the heat shrink tubing. Now, batteries don't do very well if they get over 110 degrees Fahrenheit, which is about 40 degrees Celsius. That's actually the default setting for this thermostat, okay? But I'm gonna bump that down just a couple of degrees to 38 so that the box should start cooling before the battery reaches that critical temperature. So to program the thermostat, hold the up button for 3 seconds. Once it flashes, use the up and down buttons to set the temperature to 38. Let it reset and then hold down the down button for 3 seconds. And when that flashes, use the up and down buttons and you can set the temperature to something like 26 or, just make it maybe 10 degrees less. But what that does is when the temperature reaches 38, the fan's gonna kick on, and then once we have cooled it down to whatever the down temperature you set, that's gonna shut the fan off. And that's it, guys. If you've got any questions or comments, please post those below. I used to use this rig for when it was the smaller inverter for things like camping and stuff, but I wanted to go ahead and upgrade it so that I would be able to use it for remote video shoots. And it powers my video camera, teleprompter, a reference monitor, and my laptop. With all that plugged in, I've got plenty of headroom for things like charging my phone or even running some LED lights. And I can run a full day of shooting off of just this one battery. So I picked this tool chest because I needed something big enough for a full-size solar panel, right? So the whole thing is self-contained, but I also wanted to be able to expand it and add additional batteries as needed. All of the components used in this system are linked to below, including one special link that'll add all the items to your Amazon shopping cart with just one click. Don't forget, for more off-grid and survival-related tutorials, visit us at omegasanctuary.life.